what you gotta do, drink water and be
I would not lie to you. I may not tell you everything about my life, but I'm not gonna lie about my age. Why would I do that?
So
That's dumb.
we just gotta keep running and drink water.
Why you wanna know my age?
Well, I do need to get back into running.
Yeah, exactly.
I love running. I just get back into running.
Let's do a 5K.
You can tell who you're messing with, bro. No. You don't understand these days, bro. In middle school, couldn't look right. Imagine.
I
There's 20 years old like 30 years old. Other than that.
I look younger than I am.
Your goals was made it.
But my gray hair and my real hair.
No, you gotta get like
I've had this kind of hair for the last 10 years.
you gotta talk to Dr. Shingles. We need to talk to Dr. Shingles. He got that
You should do an Ironman.
You look 35.
You're still young enough.
You can whole beer.
Maybe one day, but right now it's really not that important to me.
You don't look old, you look
That's fair.
Like doing athletic contests, like races and stuff. I mean, I've done races before. I actually trained for the Donna half. Let's see, how old is Joshua?
I never heard of shit
10.
like
So
Who's Joshua?
that was 11.
You look like you've
He's
been
my 10-year-old. So you know, I got 5 kids. I got
You actually
2
probably you had to call the police
20 and 19.
outside his class.
Then we
Nah,
took a
you
break,
look
and then we had
35.
some
He's
more.
not wrong.
10, 9,
What is this?
so I
You
was
look like
training
a
for
college.
the
I
half
can see
marathon.
a
I can see you in college. I can see you.
And I was ready, right?
You look at thug right now. I would see
For the race.
I can't talk, so.
I would see you in the street corner. He looks
Six,
different.
like there's no possibility that I
He does
could
not look like a
possibly
young
run.
man. He would not look
the
like
next
That
day.
sucks.
I was so bummed.
Buddy, I guarantee
look
you,
aged.
if you go to Publix and you ask for a free cookie, they're gonna be like, get the hell out of here.
But I'm just 14, man. No, you're not.
I
don't look that old.
trained by running long distance.
I don't look aged. You're
I
definitely
said,
college
like,
student. You look like a college student.
I
Y'all
don't
are
do
so
You look
loud.
like a college student.
average like a 5-mile
You look
run.
past as a college
Like
student.
that would be like a light day because the total race is like 13.1 miles.
I know he didn't
So I
just
would,
call
like,
5
work out,
miles
you
a
know,
light
to
run.
do like
My
a
dad
8-mile run, a
has
10-mile run,
13
a
Ironmans.
13-mile run.
What is an Ironman?
It's a 40 miles,
Y'all see the Jaguars?
Alright guys,
100
physics, here we go.
7-mile bike, and then
So,
a marathon run.
Mr. Minnie, you can swim.
No,
What?
Racist.
No,
I mean, if you want to play the Cuban card, yeah, I can swim.
He's cute.
I can swim. There is a joke that if you're Cuban, then you could have swam across to the country.
I can't do this anymore.
Oh my goodness.
I swam over
I
here.
didn't say he did that.
I float, I don't swim. I just don't sink. That's the goal.
Really need to focus here.
Okay, we're locking in. We're locking in. It's 1:30, chat.
150?
1:30. Oh shoot! Y'all, I need glasses, please. Not too much. I can't see.
Mr. Mayor,
I swear that was a 3.
So I was telling Dana that my dad has done 13 Ironmans, and she was like, Mr. Mayor, you know how to swim? And like after I explained to her like what the swim, like it's a swim, bike, run.
I float. I just don't sink. I can swim. I don't sink.
Oh, alright guys. So, let's continue. So, we've already talked about how the electric field is in the same direction as the force on a positive test charge and opposite for an negative charge. We also have talked about how a charge will change the property of space, making the electric field around it. And we also kind of compared like the mass and the charge and the field. So the field lines, if we go back to that aspect of it, actually I don't want to do that quite yet, but what if we want to find, okay, like let's say we've got a big source charge Q. So we've got a charge, we see that around it there's an electric field, and I want to know, okay, well, what is the electric field strength a certain distance away from the charge? So we don't have an equation for that, but if we were to combine these two equations, and I wrote this force equation that we talked about last class a little differently. So I'm saying that we've got the small test charge, let's say Q right there, and the big source charge, big Q. So the big Q is going to be the charge that creates the field in the space that we're investigating. Okay, so that's why I wrote it like that. It's still Q1 times Q2, but I'm going to substitute this into there. So when I do, we got K, Q over R squared divided by Q, and then as I fix my complex fraction, which we did a lot of for our lab, okay, those Q's cancel, so I'm left with a new equation for the electric field, KQ over R squared. So this is not in our equation sheet, but it is highly likely that you will still need to use it, although it was a very, very simple way to get there, as you just saw. So this tells us that if we are a certain distance away, we can measure how much electric field strength we have at any particular location. We don't have to have a charge actually there, which is one of the nice things about the electric field, is that we don't have to have a charge there to find out how strong the field strength is. It's kind of like finding how strong the gravitational field strength is, like on the planet, or what the G is. So we use this equation. Notice that the larger the charge is, the greater the field, but the further away we are, the smaller the field is. And of course, just like the force, it is an inverse square law as well. So, you might need to use this new equation on our next challenge question.
Is this the equation I should put in my calculator? Oh, wait, can I even put that in my calculator?
Where'd my mouse?
I got it. No, I'm saying I got the computer.
Alright. Oh, look! Another ranking question. You love those, don't you?
I don't. They make me
So we're we're taking apart the mountain, as you can see. I would actually like to keep all of the great bricks. Not necessarily like built in chunks, but we can take them all apart. I just don't want to resort them. So if you want to sort them, no, the first one, all
Pretty sure it's
bid, that's okay too. But
No, it can't be. E1's not
so
equal.
all of the light and dark gray pieces.
E1's not equal to E2.
E1 or E2 grade. That's the question.
That's my biggest thing right here is E1 or
If
E2.
you want to sort them out
E2.
by size, you can put them in smaller baggies and put all of them in the baggies. The Duplos, no idea. And any colored bricks, like the basic bricks, we can resort them.
Yeah, no, it's E2, yeah. So E2's the greatest one. No matter what. No.
I think it's B.
I don't know what I'm looking at.
It's equal to.
D is 1/2, so A is regular, so it's just 1.
I need
B
glasses.
is 2. C is 1/4, and then D is 1/2.
So which one is it?
So it's B, A,
Alright, so you got some answers.
DC. It says from least from largest to
So it's
smallest. Yeah.
C.
Looks like more C's now. Alright, I gotta call it done though. 3, 2, uno.
Take them down.
Done. Alright, let's take a look here. So, we are ranking these. So each one has a position away from a certain charge. We don't know if the charges are positive or negative. That's not a part of what we're talking about here. All we're finding is what is the strength, how strong is the electric field, not necessarily where it points. Okay, so if we were to just come up with some expressions here for E1, 2, 3, and 4. Using our new equation here, E1, that's going to be the K times the charge, which is just 1Q, divided by the distance, which is only 1R squared. Okay? E2, so 1R, but twice the amount of charge. So that's going to be a 2KQ over 1R squared. So if we were to pull out the extra numbers here, that would be like a 1, that would be like a 2. Okay, so far so good. 3, we've got back down to 1Q, but now we've got twice the amount of distance. So that's going to be 1KQ, but twice the distance. That 2R gets squared. That 2 squared is 4. So that's going to be 4R squared on the bottom. Pulling out the extra number, that's a 1/4. Okay? And last but not least, our 4, we've got twice as much charge and twice as much distance. So we've got a 2KQ divided by, again, the 2R is squared, so that's going to be 4R squared here, and the 2/4 reduces down to a half. So that means that our E2 is the biggest, E1 is next, E4 is next, and then E3 is last. So 2, 1, 4, 3. No ties though. No ties. 2, 1, 4, 3. C is the correct answer.
We got C. We got C.
Yes.
At least I got it last week because I kept.
There you go.
And I was about to forget, but well.
Alright, so let's see who is the first C. Looks like Nishant, did he change his answers? No, he did not. Team Tara taking first place. Very good. Let's see who is next. We've got a perfect changing his answer. So Quantum taking second place. And then we've got the Spice Girl taking the next place point. Good, good, good. Alright, so now let's talk about field lines. Okay, and the rules for our field lines are going to be the same things that we saw before. If you look in your books, they have really good pictures, better than I can draw, that is. 449.
What's this thing? Oh, no, it's over.
449. My bad. Going the other way. Yeah, so you can see that there's some really good pictures here, but they actually give you two, one for the positive charge and one for the negative charge. Okay, so our rules that we learned before are still valid, right? The field lines will go out of the charge like spokes on a bicycle wheel. They're never going to cross. They always meet the object at a right angle if we were to zoom in. The distance between them is proportional to the electric field strength. So the stronger the field is, the closer the field lines are together. But we have a difference now. So we could have a positive charge, and we also could have a negative charge as well. Okay. Remember that the number of field lines that come out of it goes along with how much charge it is too. So like if this is a positive 2Q and this is a minus 1Q, the positive 2, the 2 is going to have twice as many field lines that come off of it than the 1. Okay, so again, that's going to show us the stronger field strength at the same distance away. But the directions are different now. Like, remember with our mass, there was only one direction because the force acting on a small test mass was pointing towards the mass. So the gravitational field always points towards the mass. But here, we're going to use that same rule that we learned at first. Okay, well, let's use a positive test charge and see where does the force point. And then that's where the field points as well. So we see here that there's going to be a repulsive force. So that force on the test charge is away from it. So my electric field surrounding a positive charge always points away. Conversely, if we do a small positive test charge around a negative charge in that field, we see that there's an attractive force. The force points in. So the field lines always point in to the negative. All right, cool. Now, on the next page of your book, page 450, we see pictures of, well, what happens if we have two charges close to each other. So the first one shows that the field lines kind of like spread apart, like away from each other. They're not going to cross, but they also don't meet as well, because both of these sets of lines, they're going to either try to go away from both of them or towards both of them. Okay? But the next one shows you an electric dipole, where we have one positive and one negative. In this case, they are equal, and you see that it's nice and symmetric. But the really cool thing here is that the field lines will actually flow from the positive to the negative. Here we have unequal charges, and so the shape of what we see here is kind of wonky. But if they're equal, just like they show you in the book, the shape is nice and symmetrical, which is cool. So the field lines will always flow from the positive to the negative. That'll come up sometime in the future as well.
Not too much.
All right. Now, remember that as we talked about the gravitational field, there was a point where we zoomed in, right? So we zoomed into actually standing like on a planet, where if we zoom in here, we see that, well, the curved surface of the planet really kind of looks flat, doesn't it? Like if you just look, I see flat, I don't see curve, okay? But if I zoom out, I see curve. Just like if you were to graph a circle on your graphing calculator, but then you zoom in, it eventually looks like a line. Calculus, yeah. But in terms of our field lines here, if we zoom into the surface, we'll see that our field lines are equally spaced. So that gave us a uniform gravitational field in that region of space, which allows us to assume that G is 9.8 as long as we're close to the surface of the Earth. Okay? Same thing happens with electric field. Okay? So the electric field, if we zoom in to a big charge or a small charge, just with like a scope or something, but if we zoom in, we find the same thing happening. Okay? Like let's say that this is a giant positive charge. We've zoomed into the surface of it. The field lines will just look like up and down lines, but the real question is, will they point up or will they point down?
Neither.
No, they will point up or down. If it's a positive charge making these field lines, and we know that the force acting on a positive charge tells us where the direction points.
Opposite from
It has to point up, yeah, because this is a repulsive force, so therefore the electric field lines will point up or away from the positive charge. And if we were to flip it, then they would go down because it's an negative charge. Now, we can artificially make this. Okay, so let's say we've got two pieces of metal. Okay, parallel conducting plates, and we hook a battery to it. This is our sneak peek into circuits. Okay, so we hook up a battery. Now, you guys know that a battery has units of volts. Yes. So this is voltage or the potential difference. So I'm going to hook up a battery. So technically, a battery symbol is like that, which we'll learn here soon too. So there's going to be a voltage, and there's going to be a positive side to the battery and a negative side. So the positive side, now this is not a complete circuit, so current's not going to be flowing, okay? But the piece of metal that's attached to the positive side, it's going to draw electrons away from the piece of metal and into that side of the battery, causing this metal to have a net positive charge. We talked about how we can move charges around last class with the electric force and how we charge things. Same thing happens here, is that the electrons in this wire are going to be repelled by this side of the battery, and so they'll have more collecting over here. So we've got a setup where we've got two oppositely charged conducting plates, okay? And we've got, well, in this region, it is going to set up an electric field, okay? This is actually one of the capacitors, okay? So the field lines are going to be straight up and down, and they're all going to be equally spaced inside that region, so we've created a uniform electric field. Our next equation here tells us that if there is a distance d between the two plates, and a voltage V is applied to those plates, then we get, it doesn't matter where in this space we are, everywhere in the space has the same electric field strength of V over D. Easy peasy. All right. Next challenge question. Here we go. This is actually an IB style question, since we're leaning more towards IB as we learn stuff now, because we're all done learning for the AP Physics 1 exam. And you'll see that it's got two parts to the question. Yeah, towards the end.
Weren't you gonna talk to us about like everything we'll be doing next year?
I'm sorry, what?
Like, I was gonna ask, like, didn't you tell us like what we're gonna learn next year so we can continue?
I can.
What would we learn
Well, let's talk about that later.
later?
Yeah.
I say.
I put B.
I also want to
If everybody
be,
wants to be
so I already know who's IB in here. Got a lot of them.
I say B.
We didn't talk much about what if the direction that goes. Wait,
It's not like
literally
it's
trying-
It's totally B. I already put B.
Does it tell us where the
Actually, it puts you learn this? It puts more pressure when you go from 5 down. 5, 4, 3, 2, 4. Yeah, well, it's
Yeah, I think
that's okay.
Alright, we got lots of B's, buzz. There's an A, there's a C. No, that A changed, okay.
what?
And then that B changed to a B as well. Okay, so it looks like these are the popular answer here. I'm gonna call that done.
Okay.
In 3,
So what do you B?
2,
You know what? I thought I.
1. Done. Oh, he changed it back. Alright, here we go. So, we've got 2 plates. Oh, so check it out though. So it is stationary halfway between 2 horizontal charged plates. So we've got a negatively charged particle. Now, we don't know how the field is going here, okay? But we do know that there is a field in this region of space here. So if we look at it, so here's our particle, and in order for this to be stationary, knowing what forces are acting on it, what forces are acting on the charged particle here?
Positive?
Negative charge.
Would it be
Equal
positive?
positive and
Let's try that again. What forces, like, what's one force?
Right.
Gravity. That points where?
down.
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 I think so, spark.
Okay, now there is an electric field here, so there will be an electric force as well. Okay. In order for this to be stationary or floating, where does that force has to point?
Up.
It has to point up.
To cancel. Okay.
So if the electric force has to point up, but it's a negatively charged particle, where does the field have to point?
Up. Oh wait. Down. Because
I don't
it's
want it to be
opposite.
down. It's up now.
Remember, the field points in the same direction as the force if it were a positive charge. But this is a negative charge.
It has to point
So
down.
if the force points up, the field has to point down.
He said
The
DB.
field has to point down.
And
Okay,
he said
so that means it's either C or D. Sorry, bees.
I told you.
The next part though, so what is the magnitude of the field? So we have our equation V over D. We are given the fact that it is exactly halfway between the two plates. But this is a uniform electric field. The E is the same regardless of where we are in the field. So it doesn't matter if we're halfway or right up here or right down there. It's going to be the same V over D. So D is the correct answer.
I was half right. You said B on a form of apology.
I know you
Well,
read.
what's the freaking
Sorry, Martin. That's a bit too late there.
You said B last.
Sean
Told you to be down. Yo,
said
buddy.
B, and then
Martin,
he
there's
said
no
D,
way.
that was
There's no
illegal. Then he said B again, and then he said D again, which was for sure. Alright, but that's the only D that I have. Team Tara gets all 6 points.
Yo, what?
Good job.
Tiny bit of water.
Alright. Almost done, guys, almost done. So, remember last class we also talked about how if we had a system of charges and we had forces that were acting from multiple charges that we drew where the forces were, we could combine them in 2D to find where our force points. We can do the same thing with the electric field. So let's take a real quick look here. We'll see our last challenge question and then we'll be done. Okay, so let's say we have a positive 2Q there and a negative 1Q here. Okay, and I want to know where is the electric field at different points. Let's say this particular point, right in the middle. Where is the electric field pointing? So what I have to do is I have to find where the electric field is pointing in this spot due to this one. I'm going to draw that, and due to that one, I'm going to draw that as well, and then I'm going to add my vectors together. All right? So here we go. So at this position, we know based on this positive charge, where will the electric field point if it's right here compared to it?
That way.
It's going to point to the right, okay? And since these are equidistant from each other and comparing the 2 to the 1, this field is going to be twice as strong as this field.
Okay.
Okay, because they're equally distant, so the only difference is our charge, okay? So we're going to say that E due to the positive is going to point to the right, all right? But I still have to address this one. So at this location, where is the E based on that charge pointing?
To the right.
To the right as well, right? Because the field lines will always flow out of the positive and into the negative. So it's going to point to the right as well, but it's only going to be half as much because it's only 1Q instead of 2. So then I just add them together. That seems easy enough. So my E total is going to look like that. Cool. So I know for sure if I plug in a proton there, it will accelerate to the right because that's where the E points. All right. But what if we pick a different point? Like this one. Let's make a point not along, oh, actually, hold on. Before we get there, where do you think we should put, so there's going to be a spot along this line, either in between or to the left or to the right. There's going to be a spot where the electric fields cancel out. Where do you think that's going to be?
Other side of the two.
On the other side of the two?
Yeah.
Okay.
Right?
Who says that? This region. Who says this region? All right. Well, let's find out, right?
Wait, no, it's gonna be too good.
So,
Say it.
It's gonna go the other
if we
side.
go over here,
What?
so now we're on the left side, so the E field still has to point away from the positive, okay? But we're really close to this one, which means that our E field is big. Big and pointing to our left, okay? Now, here compared to here, we are far away from this one, so the E is small, but it's still pointing to the right. Although technically they are opposite directions, they're not really close enough that they would actually cancel. Because we're so close to the big one and so far away from the small one, the E fields cannot cancel out. But if we went over here, okay, we're far away from the big one and closer to the smaller one, those E fields will have a chance to cancel out now. So it will be over here.
Swear.
Good. All right, last one.
Basically,
What about
You're not like that.
that
you're
one?
not like him, buddy.
You're not.
You're just not like him.
Okay.
It's okay to
Where does our E field point? Here. Again, we have to deal with it one thing at a time. Okay. So at this spot, based on that one, where does the E field point?
Down.
Points down because it has to be away from the positive charge.
How?
Based on this one, which way is it pointing?
Like slanting to the right now.
It's an attractive, so it points kind of like that. So as we add the two together, the net result will kind of look like that. So that's where our E field will point at that region of space. All right. So let's see how well you use this new skill for our last challenge question.
Everybody. Oh no.
So you've got a square. There's 3 charges on 3 corners of the square. We're asking where's the E field pointing at the 4th corner.
How are we counting this? 1, 2, 3, 4, or 1, 2, 3,
No.
4?
So your options are A, B, C, and D
Oh.
in terms of where the electric field will point if you add them all together. Knowing that this one is a Q minus, these 2 are Q pluses. That makes a difference.
Yeah.
Let's see.
I put C.
Which one is? I low key think it's like
Has to be.
A.
Oh wait. Wait, I'm wrong.
Let me work this out. I can drop it.
I think it's B.
Yeah, it's either C or D.
I did. I'll just keep it at
Oh, I put B.
Jordan, or are we lost without saying? Is everybody lost without it?
here. I got it.
Oh no, that's not him. That's not him. Yeah, it's too dark. It's too dark.
Now there's
Too
C.
dark. Yeah, it's too dark. Yo. That's not one C.
Okay. I already have B put down. Yeah, because it's going to be pointing kind of up, but then tracting it, it would slant it more to the right.
Let me see you on a roll. Good old Tootsie Roll action. Alright. AB on a roll, Martin. Yes. And Jordan.
So proud
you get all A's?
A honor roll.
No, but did you get
Alright,
all A's?
this all done.
A honor roll. If you get A honor roll, you don't get
You got all A's, it would give you A honor roll.
Done.
Dumbass.
True. That's how that works.
I never do.
Alright, here we go.
I never do that.
So, again, we have to take into account how big the charge is, what its sign is, and how far away.
Wouldn't it be farther
Okay,
away
so
it'd be
at this
less-
location,
less
from
something
this guy,
more
the
something
E
is that?
field has to point towards it.
But you got AB?
Okay. Now
But the one all the way
here,
down to the
it's
right.
going to have to
it would
point
have less of an
away
effect.
from the positive, but it's a little further away because
Okay.
this distance is longer than this or this.
ABC,
right?
but
Because
here
it's a square.
it's not.
So it's going to point up at an angle, but not as long as this guy is. Okay? And then from here to here, this is going to have a field pointing up, and it's going to be equal to this one, just pointing up instead of to the right. So if I were to add up all three of these, again, it's just pictures here, no numbers, but if I were to break up that one added angle into its two components, okay, so notice that I've got two ups, so that up plus that up gives me a bigger up. Okay, and then a right minus a little left gives us a slightly less right, and as I add those two together,
We're third.
looks like B to me. B is the correct answer.
Absolutely.
Yes.
No,
Alright, let's see.
Actually, I might be safe. Like, I might choose
Sean changed his answer.
Buddy,
No,
you're as
not.
good as, like,
Tara
the AI
taking
they gave
first
me on the
place.
computer, bro.
They are on fire today, guys.
we might have been.
See?
friends.
He's
Followed
like
by,
that
let's
he's
see,
AI.
Perva changed his answer. Yes. Team Quantum taking second. And
might have
we
been
got,
point.
let's see, what's our next one?
You know, I just, hey, bro.
Yeah, no, it came in with a slash. Yes, it came in with a slash. But that was your first thing.
Yeah.
Yeah, so that's fine. Yeah, so
I
Team
thought you
Spectrum
changed his
taking
answer.
third
I
place.
put the answer as you tell me it.
Very good, guys, very good. Feel free to take 5. I know that we used some of our pods time at the beginning because we were talking about different stuff.
Very important.
But we still have time in class for pods, so there you go. So feel free to take 5. Then once we come back, check out those pods. The quiz is all already up in focus. If you wanted to talk more about possibilities for next year's classes, we can do that as well.
Can I go to the bathroom?
Go ahead.
This ain't time, right?
And we are done with our teams.
Oh, wait, you are so adorable. Wait,
Okay. Push.
what, is he delivering a baby?
Whoa.
Oh my god. Closing the goddamn door. No, it's much better to face these kinds of things. Well, as a poison rationality, I chimed in. Haven't people ever heard of closing the goddamn door? No, much better.
Let's
in front of Mr.
cruise
Maynard.
on those words, shall we?
The disrespect. You not even to hide it.
It's hard to change the lyrics of a song when you're into it.
At least have some respect and hide it.
It's okay. I know that not all people share my standards.
Come on, Tracy.
As
Dance, nigga.
long as it's, not blatant.
The N word.
Yeah.
My fault.
Yo.
Me, bro.
And you get type job.
I chimed in with the haven't you people ever heard of? Closing the goddamn door. No, it's much better to face these kinds of things. We'll test the poison rationality.
I'm about to lose my mind.
Haven't you people ever heard of? Closing the
Y'all gonna make me.
He leaves.